Hi, so this is a video on section 3.3, which is on multiplication, and we're going to look at all different types of ways that we can teach multiplication in elementary school. We're really going to look beyond just the standard algorithm that you're probably used to using and really dive deep into different diagrams and pictures and just other different types of algorithms that are helpful for students too. So let's jump in. So we're going to start by just talking about the basic idea of what multiplication is. So I think sometimes it's easy in math to look at all of these different types of concepts as separate, isolated concepts, but in so many cases they're not. So multiplication is really just repeated addition. And I think that once students understand that, then they no longer are scared of multiplication. They just realize, hey, like I've been doing addition. I'm hopefully pretty good at it. But even if, they need to practice with addition, at least they can view multiplication as not necessarily this new thing. It's just a new way of adding. So for example, 5 times 2, what does that mean? It basically means take 5 and add it twice. So you can write 5 plus 5. So this is saying I want 2 groups of 5. The other way that you could think of it is I want 5 groups of 2. So you can add up 2 plus 2 plus 2 plus 2 plus 2. And I think depending on the student, I think, some students are only comfortable going in one direction. So for example, like whatever the first number is, they always look at that as the number of groups, or the second number. It really doesn't matter, but some students feel more comfortable doing it the same way each time. Some students are okay switching back and forth. I like to encourage students to choose, like, what are you better at? Are you better at adding 5s? Because you could do 5, 10 real easily. Maybe that's faster than doing 2s, or maybe they count really well by 2s. So doing 2, 4, 6, 8, 10 is faster for them than doing 5 plus 5. So it's really good to encourage just the exploration and trying different things. And you can see below here, you could also use the number line. So, you can, if you had a number line provided, you could just, hop to 2, count in 2s 5 times. So 2, 4, 6, 8, 10, and get to 10 that way. So try 7 times 4. So what does that mean? So it could mean we're going to do 7 4s. So 4 plus 4 plus 4 plus 4 plus 4 plus 4. I got to count. That's 6, and then one more, and we get 28. Or I could add up 7 4 times, and I could also get 28. Some students might say, well, it's faster to do the 7 plus 7 plus 7 plus 7. Maybe if you're really good at adding 7s, but if you're really better at adding 4s, it might be faster doing it the other way. So both are great. The next way that we're going to talk about is, it's called a rectangular array, and this is a picture, a visual way of multiplying. So one thing you can do is draw a rectangle, have students draw a rectangle, and it doesn't have to be to scale, but if it can actually represent the numbers accurately, that's helpful. So what I mean by that is one side we're going to label with 5, the other 2 to represent 5 times 2, and let's try to make it so that there are 2 boxes on this side, and we're going to try to make 5 on here. So we've got 5 across and 2 down, and all together we can count how many we have, and we end up getting 10. The awesome thing that I like about this idea is that students start, like in kindergarten and pre-K, a lot of times they'll start even counting with these arrays, and so if they can start with counting, by the time they get to multiplication, these arrays will hopefully be pretty familiar, and it'll just be an extension of what they've already been doing. So 7 times 4, same thing. So we're going to make it a rectangle. That's going to be 7 times 4. So I'm going to try to squeeze in 4 here. And again, they don't have to be to scale. The whole point, though, is just that hopefully, you get 4 in. You try to make them the same size. You do the best job you can, but especially if kids are drawing these, they're not going to be perfect. So 1, 2, 3, 4, 5, 6, 7. Okay, so you can see that doesn't look, whoops, that doesn't look so great, but you get the idea. 1, 2, 3, 4, 5, 6, 7. Awesome. And then if we count it, 7 times 4, if we count all of those blocks on the inside, we end up getting 28. Another thing you could do with kids, which would be even better, gosh, sorry, my eraser is going crazy today, is have them use blocks. So you can use base 10 blocks, use the unit blocks, and have them give them 10, or have them make a rectangle that's 5 by 2 or 7 by 4, and then they can count the unit blocks on the inside. And for a lot of kids, that'd be easier than even drawing. So another visual to add on to the number line and the rectangular array is a tree diagram. So I think this is a diagram that's helpful probably in the later elementary school grades, just because it's a little bit more complex, but it can be handy. So take, for example, suppose that you order lunch and you have the choice of 5 different entrees. So you can get chicken, beef, turkey, fish, or vegetarian. Okay, and then no matter what you choose for entree, you have 2 types of sides to choose from. You can choose a potato to go with your meal or a salad. So we could draw a tree diagram to figure out how many different possible lunches you can order. So at the top of the tree, this represents kind of where you start, and you could go down each of these 5 branches. So you could order chicken, you could order beef, you could order turkey, you could order fish, and you could order vegetarian. No matter which one of those branches you go down, so let's say we go down chicken, then we could do potato with that or salad. With beef, you could do potato, salad. Turkey, you could do potato, salad. Fish, potato, salad, and then vegetarian, potato, salad. And then if you want to count the total number of possibilities, all you have to do is go down each path. So you start at the top and you say, well, I could do chicken and then potato, that's 1. Chicken, salad, that's 2. 3, beef, salad, 4. 5, 6, 7, 8, 9, 10. So there are 10 different possible lunches. This diagram helps us figure that out. We could have just did 5 times 2 at the beginning, but I think it's a lot harder to see why that makes sense. I think the diagram kind of pulls it all together. So next, we're going to use our base 10 blocks. So we've been using them quite a bit. We're going to continue to use them through multiplication and division and beyond. So let's just recap here. So we've got flats, which are worth 100 because we're doing base 10 here, not different bases. Longs are worth 10. And then units are worth 1. And so if we want to do 286 times 3, essentially what this means is 3 groups of 286 each. So I'm going to draw 286 and I'm going to draw it 3 times. So I'm going to draw, that's 100, 200, 10, 20, 30, 40, 50, 60, 80, 70, 80. 1, 2, 3, 4, 5, 6, 7, 8. So 8 tens is 80, and then 1, 2, 3, 4, 5, 6. So that's 286. And then I'm going to do it again. So 200, 1, 2, 3, 4, 5, 6, and then I'm going to do it a 3rd time. So if you're thinking, gosh, this is so cumbersome, the idea here is not quick. So eventually our goal is quick. Eventually we teach kids how to do things using algorithms that make things faster, but right now to lay the foundation, which is the main part of elementary school, is really just deep understanding. So we want them to understand what this means way more than we want them to just arrive at an answer. So 3 groups of 286. Now how do we find our answer? Well, just like before when we were doing base 10 blocks to represent numbers, we're going to regroup. So we're going to add all of these together. So we're adding, basically. We're taking all of these and saying, okay, let's add up all of these blocks together. What do we have total? So I'm going to make some groups of 10. So I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So here's a group of 10 ones. So I'm going to make a long because a long is worth 10. Okay, cross those off. 1, 2, 3, 4, 5, 6, 7, 8. I don't have any enough for another group of 10. So I'm going to write 8 down here because I have 8 units left over. And then I'm going to count the longs. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Got a group of 10. 10 tens is 100, so that makes a flat. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, that makes another flat. And then I've got 1, 2, 3, 4, 5 longs. I don't have 10 of them, so I'm just going to write them down here. I've got 5 leftovers. I can't make another group. So now I'm going to count my flats. 1, 2, 3, 4, 5, 6, 7, 8, and I've got 8 flats. So I've got 858. And then certainly when you're finished, if you want, you could do 286 if you're familiar with the standard algorithm. 3 times 6 is 18, carry the 1. 3 times 8 is 24, plus 1 is 25. 3 times 2 is 6, plus 2 is 8, and we end up getting 858. Now, again, that was way faster using the standard algorithm, but I can't tell you how many times. I mean, I would say most people that use this are not thinking about what it means. And I think the whole carrying business tends to get confusing, especially when you're multiplying with more than one digit. But let's look at this next problem. So 189 times 4. This would be a great place to pause the video and try it on your own. So I'm going to draw 4 groups of 189 each. So 100, 2, 3, 4, 5, 6, 7, 8, 80, 9. Probably should have made numbers that are smaller. 180, 2, 3, 4, 5, 6, 7, 8, and then 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, okay, so now I'm going to regroup. So I'm going to get my different color, and I think that's helpful to do with you as well if you've got some, crayons or markers or something. So I've got a group of 10 ones. I cross those off. I make a long. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I've got those, and I make a long. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Cross those off, and I make a long. 1, 2, 3, 4, 5, 6. So it looks like I have 6 left over, and I write that down here. I will say, just real quick, it's probably helpful if you want to even use the standard algorithm first, so you get your answer. So 9 times 4 is 36, and then 8 times 4 is 32, plus 3 is 35. 4 times 1 is 4, plus 3 is 7, just so you know what you're aiming for. So I'm aiming for a 6 here, so that way when you get a 6, if you got something different than a 6 for ones, you could stop at that point and then fix your work there. Obviously, students, when they learn multiplication, they're going to learn the base blocks before they learn the standard algorithm, so they're not going to do this. But I think for your sake, just practicing, this could be a new method for you. I think that helps. So let's count the longs. So we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, we've got a flat. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And we've got another flat. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And we've got another flat. And then 1, 2, 3, 4, 5. It looks like I have 5 longs left. And that's what I should have. So we've got longs, units, and I should hopefully end up with 7 flats. So let's see. So we got 1, 2, 3, 4, 5, 6, 7, and I do. Awesome. So 756. So hopefully you get the idea. Now keep in mind, these would be really easy to make up on your own. So if you feel like you need more practice, you could easily make up a multiplication problem and then try to draw the picture for it. Or if you have a set of base 10 blocks lying around, you could use the actual blocks, even better. So let's go down to our next method. So partial products, this would be, so if students usually start learning multiplication in 3rd grade. So they start their multiplication facts. So like basic, like what's 2 times 3, basically everything up till 10 times 10 or hopefully 12 times 12. And then once they know their facts, then they start doing multiplication using visual methods like repeated addition, the rectangular arrays, and then the base 10 blocks. And then once they're to the point where they got a handle on that, and we're sort of heading in the direction of teaching them just sort of the regular, the standard algorithm, partial products is part of that. So this is a method you can use even instead of the algorithm. This method is great because it shows you how the multiplication is being done. It breaks it down, whereas the regular algorithm, when you're carrying and stuff, you're really not thinking about what you're doing as you're doing it. So how does this work? So we're going to start with 17 times 13, and what you do is you start with any of these numbers. I'm going to start with 1, but know that when I do this, you can actually do it in any order and you'll get the right answer. Ask yourself, what does this 1 represent? It's in this place value. This 1, since it's over here, is the tens place, so this represents 10. So what you're going to do is you're going to take that number and you're going to multiply it by that number. So this 1 represents a 10 since it's in the tens place. So I'm going to write 10 times 10. So 10 times 10, and that's 100. Okay, now I'm going to keep with this 1 and I'm going to multiply with the 3. So this 1 represents a 10 because it's in the tens place, times 3. This 3 is in the ones place, so it's just 3. So that's going to be 10 times 3, which is 30. The goal is we're creating these math problems on the side that you should be able to do in your head, okay? Not with a calculator. That's the benefit of this method also. So now we've multiplied this 1 with the 1 and the 3. We're trying to combine all the numbers with each other. So now we're going to do the 7 and we're going to do the 1 and the 3, and then we'll have made pairs with everything. So the 7 times, remember this 1, since it lives in the tens place, is a 10. So 7 times 10, okay, is 70. And when you do the partial products, this is optional to write all this down. I'm writing it down so that you can see what I'm multiplying. And then we're going to do the 7 and the 3 together. So 7 times 3 is 21. Now what we're going to do is we're going to add those all up. So you add up this column, you get a 1, you get 7 and 3 is 10, plus 2 is 12, carry the 1, and you get the 221. So that's the right answer. Okay, now keep in mind, I'm going to do the standard algorithm one time just so you can see the difference. So if we're multiplying using the regular algorithm, 3 times 7 is 21. So you put the 1, you carry the 2. 3 times 1 is 3, plus 2 is 5. Now, why do we add the 2? So we're not really looking at the place values here. This is really just using tricks that end up working. We put a 0 here for a placeholder. I guess the other question for that is why. Okay, so that's another place that's kind of weird. Now we start over here. 1 times 7 is 7. 1 times 1 is 1. Now we luck out that we don't have to carry again, because if we did, then we'd have to cross off this number and put our other number there. So that's the other downside of carrying, is it gets messy and it's easy to mess up. So now we add, which is similar to this method above. 1 plus 0 is 1, and then 7 and 5. Oh, did I do that wrong? I think I did. What did I do? Oh, I think I forgot to write down the 1. Yep, 1 times 1 is 1. There you go. I just made a mistake. And so 7 times 5, actually I shouldn't bring that down. 7 plus 5 is 12. Carry the 1, and then we get the 221. So we get the same answer there. Let's go to the 36 times 75. So again, I'm going to take the 3 and I'm going to multiply it by the 7 and 5. And then I'm going to take the 6 and multiply it by the 7 and 5. But I'm going to not write down 3. The 3 is in the tens place, so that's going to be 30 times 70. Now here's how you do it in your head. You write down the zeros first. So 0 and 0, 2 zeros. 3 times 7 is 21. So 30 times 70 is 2100, or the 3 and the 7, and then add the 2 zeros. So now we're going to do the 3 and the 5. So 30 times 5. Okay, write down the 0, and 3 times 5 is 15. So you get 150. 6 times 70. 6 and 7 is 42, plus a 0. So 420, 420. And then last but not least, 6 and 5. That gives us 30. And then I add this all together. So 5 and 2 is 7, and 3 is 10. 4, 5, 6, 7, and I'm left with 2,700. Okay, pause the video and do the next one on your own. This one's the hardest. You've got more place values here. So I'm going to start with the 2. So that would represent 200 since it's in the hundreds place. So 200 times 80. 2 and 8 is 16 plus 3 zeros. So 16,000. And then I'm going to do 200 times 6. 6 and 2 is 12, plus 2 zeros, 1200. Now I'm going to do 30, since it's in the tens place, times 80. 30, 80. 3 and 8 is 24 plus 2 zeros. So notice we're only multiplying numbers that end in 0, so it makes it so much easier. So now we've got 30 and 6. 3 and 6 is 18 plus a 0, so 180. Okay, and now I'm going to do the 6. So I did the 2, the 3, and now the 6. So 6 with the 8, so 6 and 80. So 8 and 6 is 48 plus a 0. And then 6 and 6 is 36. And then now I add everything up. So I add up all this column, I end up getting a 6. I add up this column, so 8 and 8 is 16, 17, 18, 19. Carry the 1. 2 plus 1 is 3. 7, 8, 12, carry the 1, 6, 7, 8, 9, 10, and then we're left with 2. So 20,296. So definitely a little bit longer, possibly, than the standard algorithm, but especially if you have these grid lines here, I don't think it's more complicated. If anything, I think it's simpler. Okay, so here's another method. So it's called the lattice method. I'm sure some of you, if not all of you, have seen this before. If you've been to school recently, then in the K-12 system, then you probably are familiar with this. If not, then no. But the lattice method is a method that a lot of students will use to replace the standard algorithm. So instead of doing 17 times 13 and lining it up and multiplying like you're used to, they'll use the lattice method, which uses a box to organize the answers. So, and this is how it works. So you write the numbers on the outside. So 17 and 13. And then you're going to draw your box. Okay, I have one provided, but you can just draw one. And then you're going to use diagonal lines. It's called the lattice method because it looks kind of like lattice. And then what you're going to do is you're going to multiply each number by the other number, and you're going to write the result in the box. And the lattice is going to break up the tens and the ones digits. So 7 times 1 is 7. So you're going to write that on the right hand side, and if you want, you can put a 0, placeholder 0 there. So 7 and 1 is 7. 7 times 3 is 21, and you're going to write it like that. 1 times 1 goes in this box, is 1. You can put a placeholder 0 there if you'd like. 1 times 3 is 3. Put a placeholder 0 there also. And then what you're going to do is you're going to add up just the diagonals. So this box goes here, and then we've got a diagonal here, and then we've got a diagonal here. Okay, so the 1, you just carry it down. 7 and 2 and 3. So 3 and 7 is 10 plus 2 is 12. And then you're going to carry on the next lattice column. 1 plus 1 is 2. And then you can bring down the 0, but we don't need to write it down. And then the way that you interpret your answer is you start over here and you work around. So it's 221 is the answer. Okay, let's try the next one. So we've got 236, and then you've got 86 on the side. There's nothing that says you can make that you have to make your rectangle this way. If you want to do it where 86 was on the top, where it was a 2 on the top and 3 on the side, that would work also. So you're going to make your lattice lines, your diagonal lattice lines, and then let's multiply. So 8 times 6 is 48. 6 and 6 is 36. 3 times 8 is 24. 3 times 6 is 18. 2 times 8 is 16. 2 times 6 is 12. And then you're going to add down these diagonals that way. So 6, you just bring it down. 8 and 8 is 16, 17, 18, 19. Okay, so you write down a 9, and then you carry a 1 on the next diagonal. So we got 8, 9, 10, 12, carry a 1. So 6, 7, 8, 9, 10, carry a 1. 1 plus 1 is 2. So we end up getting 20,296. I find that most people have strong feelings one way or the other about lattice. Totally fine if you don't like it. You're not going to be, going to have to use it every time you multiply. But I do think just try to keep an open mind, because I've seen kids before who just, I mean, the light bulb turns on when they see this. It just really resonates with them, whereas the other algorithm, the regular way, doesn't. So, just something to keep in mind. Okay, so like we talked about with addition, we're going to talk about some properties, and some of these are repeated. So these properties for whole number multiplication, these are a grade 3 Common Core standard that students understand these properties, and so it's important that we go through them. So closure property, this is the same idea as addition. It just means that when you do an operation with whole numbers, you're going to get a whole number answer. It works with addition. So for example, like a whole number plus a whole number always equals a whole number. It also, it doesn't work always with subtraction, because think about it, you could have a whole number like 5 and subtract 20 and you get negative 15. Well, negative 15 is not a whole number, so the closure property does not hold for subtraction. With multiplication, it does. So anytime you have a whole number, let's say, for example, let's say you had 5, okay, times 10, they're both whole numbers, you get 50, which is a whole number. So you will always get a whole number answer when you're multiplying whole numbers. It does not work with division, because say for example you did 5 divided by 10, which you could write like this. Well, that's a fraction, that's 1/2 or 0.5, and that is not a whole number, so division would not work. With the division doesn't satisfy the closure property. Commutative property. So think your commute to work or commute to school. So you go to school, you you stay at school, and then you come back home, and it's usually the same route. Not always, but you can think of it that way. Commutative property means you have the same numbers, just different order. So for example, 5 times 3 is the same thing as 3 times 5. Feel free to move stuff around because you get the same answer. Associative property means that the parenthesis placement does not impact the answer. So notice A, B, C, these variables or numbers are in the same location. So that would be like me saying, let's do 2 times 3 times 4. 2 times 3 times 4, but let's go ahead and put the parentheses around different spots and see if we get the same answer. Whoops, I should have put that around the 3. So this means we do the 2 times 3 first, so we get 6 times 4, which is 24. This means we do 3 and 4 first, so we get 2 times 12. We also get 24. Okay, so slightly different order, but the same answer. So we're allowed to move parentheses with strictly multiplication, and we're allowed to switch the order of multiplication. Okay, so the next one, identity property. So we talked about the additive identity being 0. So for example, if you add 0 to any number, think identity is itself, the number stays the same. Okay, so that's the additive identity. Multiplicative identity is the number that you multiply anything to keep it itself. So that would be, for multiplication, it would be 1. I'm going to erase this just so we can fill in this blank here. So any whole number times 1 is itself. So 1 is called the multiplicative, it's a fun word to say, multiplicative identity. Okay, so for example, 15 times 1 is 15. Multiplying by 1 keeps the number the same. Okay, 2 more properties. So we've got distributive property. I'm sure you've seen this one before. Over addition, so when you have addition, or over subtraction. So distributive property just means that you can distribute that number on the outside, meaning 4 times 5, you can write it like this, plus 4 times 6, or 3 times 5 minus 3 times 2, and let's see if it works. So if we do the problem the way it's written in the beginning, we have to do the parentheses first. So that would be 5 and 6 is 11 times 4, we end up getting 44. If we do it with the distributive property, you end up getting 4 times 5 is 20, and 4 times 6 is 24. You end up getting 44 that way also. Now, is one better than the other? If in this case, No, I mean, it might even be faster to just do it the way it was written in the beginning. Like, why even bother using a property? It is helpful though if you have a variable. So it's good to talk about it in this case with whole numbers so that we can set students up down the road to do things like this, where you cannot combine the 5 and the x anymore. You have to distribute if you're going to simplify this expression. Well, I shouldn't say you have to. It depends on the problem, but in many problems you do need to simplify by using the distributive property. So that's that. And then last but not least, the multiplication property of 0. So if you ever forget this property, it's very easy to check it. You can use your calculator. I mean, plug in your calculator, 5 times 0, 100 times 0, 35 times 0, any number times 0. And this actually works with any numbers it's not just whole numbers, it's any number. So it even works for like negative numbers also, or fractions. All of those answers are always 0. Okay. Why? Think of multiplication in terms of groups. So if you think about the problem 5 times 2, you could think of this as, oh, I have 5 groups of 2. So that's like 2 plus 2 plus 2 plus 2 plus 2. I've got 5 groups, and then that makes 10 altogether. If you have 5 times 0, you could think of it as, okay, I have 5 groups of 0. 0 plus 0 plus 0 plus 0 plus 0. Okay, that gives me nothing. Or you could think of it the other way, where you have 0 groups of 5. Well, who cares if 5 is what's in the group? If you don't have any groups, then you're going to end up with 0. Okay, so either way, you end up with 0. So next, I got an example. It's kind of squeezed in here. Try computing 25 times 46 times 4 in your head. This is something that, I would say by, 3rd and 4th grade, students would hopefully be able to do. Think of compatible numbers. So when you're multiplying numbers that go together, okay? 25 times 4, so that's like 4 quarters is $1 or 100. So if you put those together, you end up getting 100. That makes it so much easier when you multiply it by 46. We can just do this in our head. 46 times 1 is 46. Plus those 2 zeros, you tack them on at the end. So much easier than if I had done these and actually like work that out using lattice or the standard algorithm. It would have taken a while, and then I'd have to do another problem times 4 at the end, and I'd end up with the same answer. So we're going to talk a little bit more on this next page here with mental calculations. And then this grid here, I'm not going to spend time filling it in, but I do think it's helpful. It's probably been a while since you've done one of these. Take a minute and see how much you can fill out. By the end of 3rd grade, students, let me just scroll up here, you can see the content standard. So it's a Common Core standard for by the end of 3rd grade, students should know from memory all products of two one-digit numbers. So that's basically up till 9, but most of the time they're going to be asked to do up to at least 10, since 10 is pretty easy, and then many times teachers will have them do even up to 12. Okay, so let's talk about some mental calculations. So how do we multiply? We just did a problem, but how do we multiply quickly in our head? Let's just jot down some of these friendly numbers, we can call them. So one friendly combination, 50 times 2 is 100. 2 times 5 is 10. 25 times 4 is 100. 20 times 5 is 100. And just kind of keep those in mind. So like when we look at our next or our first problem, anything with a 0 should hopefully like pop out to you, because that's going to make things easier when multiplying. If we put the 20 and the 5, 2 and 5 is just 10. So 20 and 5 is just 100. And then we do the times 37. That makes things so much easier. We can just do 37 and 3 zeros and get 3,700. Okay, how about the next one? So hopefully your eye goes to this 0 right here. And then instead of thinking it as 40, think of it as 4. Like 4 quarters is $1. 4 times 25 is 100, plus an extra 0 because it's not 4, it's 40. So we get 1,000. So 40 times 25 is 1,000, times 19 is 19 plus 1, 2, 3 zeros tacked on at the end. So I did this all in my head, no calculator. This next one, okay, so I see 25, that's sort of like a, that could make a nice number. 25 times 2 is 50, times 2 is 100, okay, you could do it that way, or you could say, oh, I'm going to put those together and make 4, and 4 times 25 is 100. You could also do it that way. And then now when we're doing the 79, piece of cake, 79 and 2 zeros to make 7,900. Okay, so the next strategy I'm going to talk about is a strategy where we make substitutions. So take this first example, 25 times 99. That would take so much time if you had to work that out. But if you need to do this quickly, it would be so much easier to just multiply by 100, okay? If you multiply that by 100, you get 25 and 2 zeros. Now, if you're okay with just estimating, so like if this is something you have to do, maybe in life, you're just estimating because you're trying to calculate how much something would be if you bought it or something, that might be fine. If you want the actual answer though, what you can do is modify. So we multiplied 25 by 100, which was too much. It was one more group of 25 than we needed. So instead of 99 groups of 25, we got 25 groups of 99. Or I'm sorry, instead of 99 groups of 25, we got 100. So I'm going to take off a group of 25 since I have 125 too many, and that leaves me with 2475. Okay. So similarly, we're going to do this one. Instead of 11, 11 is really close to 10. So I'm just going to do 42 times 10, and you get 42 plus a 0, 420. And then ask yourself, well, how did that change? So instead of 11 42s, now I only did 10. So I need to add in a 42. So this time I'm going to add a 42 because I didn't do enough. I actually brought this down. So I'm going to add a 42 to compensate, and you end up getting 462. Okay. With this one down here, ask yourself which one of these numbers is closer to a number that would be easier to multiply with. 30 times 102, that's not that simple. But if we make this 100, 34 times 100, that we can do in our heads. So 34 times 100 is 34 and 2 zeros. But I need 102 34s. So I'm short 2. So I only did 100 groups of 34. So I need 2 more 34s. So at this point, you could add 34 separately twice. Or if in your head you could say, well, 34 and 34 is 68. And then just add 68 there. So you get 3,468. So it's not that bad in terms of adding. All right, so that's how you substitute if you want the actual correct calculation, but we also want to talk about, just like we did in the last section, approximating. So this is really helpful because, I can't tell you how many times I approximate in real life. I probably approximate more than I actually multiply because it's quicker if I'm looking for a ballpark. And you'll notice right here, this is a copy of the content standards that, for NCTM, but it's very similar for Common Core. When students leave grade 5, they should be able to solve many problems mentally and then to estimate a reasonable result for a problem. Okay, so that's what we're doing here. And estimating certainly doesn't start in grade 5. It starts in grade kindergarten and moves throughout the K-12 math classes. Okay, so let's first start talking about just in general how we could round with multiplication. So let's look at the example 28 times 63. If you were to round this, and I just said round it any way you want to, how would you round it? If I were to round it, I would probably just do 30 times 60. Seems reasonable. 3 times 6 is 18, and then 2 zeros. Okay, so it asks though, why is rounding with multiplication a little bit more risky than rounding with addition and subtraction? Well, if you do 28 times 63, let's just see how far off we are. If we actually work that out, we get 1764. Okay, so you can see we're not that far off. If we were to add though, like if this was an adding problem, let's look and see what we would get if we added. So 8 plus 3 is 11. 6 and 2 is 8, we get 91. But if I were to estimate, I would end up getting 80. So with addition, I'm off by 11. okay? With multiplication, I'm off by 36. So you can see just with the exact same problem with multiplication, I'm off by more. Why? Well, multiplication in and of itself yields larger answers. So you're going to consequently, get bigger mistakes. So just something to think about when you're rounding with multiplication. If you're a little bit too lenient with the rounding, your answers aren't going to be that accurate. Or that close to the real answer, which may be fine. It just depends on the situation, and it's just good to know. So why don't you try these? So use rounding. You can make any adjustments that you feel needed. So I'm going to do 80 times 60 here. 8 and 6 is 48 with 2 zeros. Okay, not the only answer. This is just what I'm thinking. 194, I'm going to say that's about 200 times, I'm going to say 25 because I don't mind doing 25 times 2 is 50 and then add the 2 zeros. You could also certainly do 200 times 20 or 30, either way there. That would give you 4 with 3 zeros. If you did 200 times 30, then that gives you 6,000. So you can see the 25 is right in the middle. That's actually closest to the real answer, but all of those are totally acceptable in terms of rounding. So now we're going to come back to compatible numbers and we're going to combine it with the rounding. So if you take a problem like this example, how could we round this to use compatible numbers? So for example, the 4 is a friendly number with 25. 26 is really close. So if we say, all right, well, we're going to round this to 25, then we get 100. And then we get 237 times 100, which is just 237 and 2 zeros. That allows us to round. So that's our approximate answer. Let's do the same thing down here. So this would be a good time to pause the video and try these on your own. So I'm going to take the 2 and I'm going to say this is about 50. That gives me 100 times 117, which is 117 plus 2 zeros on the end. And I'm going to make sure to use my squiggly equals, which means that I'm estimating approximately. For this problem, the 24 is really close to 25, so I'm going to say I'm going to round that to 25. 4 25s is 100 times 46 is 46 and 2 zeros, so 4,600. Okay, so we're going to use the next problem we're going to do, which is the last problem, is using a very specific rounding method. So you have to pay attention to the instructions. So front end approximation, we did this with adding, just means to round by keeping the leading digit, the first digit of the number. The rest are zeros. So this becomes 40 and this becomes 70. It does not matter that this is a 3 and the 2. Those do not factor into it whatsoever. So if it was like 49 times 79, even though those are really close to 50 and 80, you would still do 40 times 70 if you were asked to do front-end approximation. The reason this method is sometimes worth using is because it just makes it really simple for kids. So this is a really good way to practice rounding that's a little bit simpler than using our traditional rounding rules where you have to look at the number to the right and see if it's 5 or greater. So 40 times 70 is about 28, 2 zeros, 2,800. Let's do this one. So this one we'd keep the 6. So 60 times 800. Okay, and again, like the 800, we're rounding down considerably here, but this is just an estimate, and this makes rounding a little bit easier if younger kids are doing this. So 6 and 8 is 48 with 3 zeros. Okay, we're left with 48,000. And then last but not least, so we've got 2 examples here. You try if you want to pause the videos and try these on your own. And then I'm going to work them out now. So we've got 200 times 70 gives us a 14 and 3 zeros, 14,000. And then a 30,000 times 400. 3 and 4 is 12. 1, 2, 3, 4, 5, 6 zeros. 1, 2, 3, 4, 5, 6 zeros. And then I can put commas in if you'd like. So it looks like I got 12 million. So that's it in terms of multiplication. Stay tuned for division.